All right, guys, let's get started. So, I got some questions, I guess, about am I going to give you guys something to think about prior to this exam I'm going to be you guys on Friday? And the answer is yeah, I'll post some stuff. I haven't done it yet, but the best place to start would be to go back and do problems from the homework that are like the problems you've already done from the homework. And then I'll add some more stuff tonight or tomorrow morning when I get a chance to sit down and write it up. Okay. I will say that the first exam in this class sort of marks the end of the easy part of the class. So I know that probably it doesn't seem for a lot of people like this hasn't been particularly easy so far, but like this class gets the way a math professor would put it is it gets quite a bit more interesting in the second half. So, and we're going to see some of that today because I'm going to talk about the sort of cornerstone theorem of all of complex analysis, which is called the Cauchy integral theorem. Yep.
The quiz that you gave us was like proof-based, obviously, not computational.
Uh-huh.
The midterm going to be like that?
The midterm is going to be largely but what I'm expecting for the midterm is that it would be reasonable for me to ask you a question that says show something, right? I'm not asking you to formally prove things with epsilons and deltas, but if I ask you to show that thing about, like, prove to me that an analytic function has path, or has, like the loop has path-independent line integrals, right? Then the way you would do that is you do the thing where you form the two contours and you integrate the loop and say by Cauchy-Goursat it's equal to 0. I would put that in the range of questions that I could conceivably ask you. But the bulk of what I'm going to ask you is going to be stuff like, there's going to be a little bit of conceptual stuff and a lot of the sort of computations that we've already done. Even some of those computations are abstract in the sense like compute a derivative from the definition, for example, right? That's an abstract idea, but it's kind of a computational version of it. So we'll see a little bit more of the abstract thinking that you need to put this stuff together as we go into the second half, but mostly it's going to look like the homework, right? It's not, I put on the quiz because I wanted to indicate that it was possible for me to ask you sort of a proof light question, but I'm not going to hit you with like epsilons and deltas, right? I mean, I actually am going to hit you with epsilons and deltas today, but you're not responsible for those epsilons and deltas. But yeah, I'll put all that stuff up on Canvas, and then if people want, on Thursday this week, we can just spend time going over all that stuff when we do the lab day. Where you guys can work on all the stuff that I put up or stuff from the book and get ready for the test and just ask. We can do it together, or we can do it in groups. That would be my intention. Any other questions like that I can answer? Yep. There is not homework this week. We've covered the material that I wanted to cover for the test, which is up through the Cauchy-Goursat theorem. That section, everyone's got homework assigned on. I'm going to start the Cauchy integral theorem this week, but that means that really the natural place, I'm going to put problems out if people decide they want to get ahead and like work on math because they're so excited about complex analysis they just can't stop. But that won't be doing until next week because we're going to do I have a lot to talk about over the next couple of lectures. So I am going to talk about new material today and tomorrow, but it's not material that's going to be covered on the exam. Anything else? Okay. So now as far as the quiz itself goes, I guess I should say, you guys can turn it in today. You can turn it in tomorrow. You can turn it by email. You can turn it on paper. If you have it to me by tomorrow in some sort of form where I can print it, I will try to have it graded by Thursday. If you don't, I guess you've got a lingering quiz that's floating around out there that's not going to be very useful for the exam. But it's not going to hurt my feelings if you turn it in on Thursday. I'll also tell you, if you want advice about what classes to take next quarter, and you're thinking, boy, this complex analysis sure is great, let's see, what else is on the calendar besides 409, then that's not going to hurt my feelings, and you're allowed to ask me for advice about other classes you might think about taking as well. Okay, so today we're going to talk about the most important theorem in complex analysis, the most. But we should motivate it before we start because we can guess. This complex analysis is amazing because we can guess what's happening before we actually do it. So here's what we know right now, and we're going to use this. So sort of the upshot of the last couple of lectures is the sort of full Cauchy-Goursat theorem, right? And its consequence, the circle contour theorem. So Cauchy-Goursat said that if you have C in its full generality, C is just closed. smooth curve in a domain D, and f is analytic on D, then the integral around C of f is 0, right? So this is removing the need for simplicity. When I say domain here, you should think, we should be careful here. I meant to write simply connected, although it's implied in a lot of the way that the textbook approaches some of this stuff. Okay? Okay, so let's see if we can motivate my claim and about this theorem being so important. And the idea is, right now, we have a lot of theorems that look like this, that say things like, if f is analytic, then stuff. Right? If f is analytic, then some stuff happens. Like, all kinds of good stuff happens. The problem is we don't really have a good idea about what the analytic functions are. If we're analytic, we're holomorphic. But if I just give you a function, the only tool we have right now to see if it's analytic is the Cauchy-Riemann equations, right? So what we want to build to is a tool that we can use to investigate, to investigate functions that we might think might be analytic. So in particular, even if you know something is analytic, I hand you a function, you put it into the Cauchy-Riemann equations, it turns out to be analytic, and then I say, well, what's its power series? It's analytic, it must have a power series. What is it? You can't tell me, because secretly you're not allowed to use Taylor's theorem yet, because we don't know it. So the idea is somehow I have to have a tool that lets me build the coefficients of a power series. That's kind of what we need now. Like, I know if analytic, then stuff, but if it is analytic, where does the power series come from? So first big question is, if f is analytic, what is the actual power series? Sort of big question 1. And big question 2 is, okay, maybe we can resolve at the same time. We know that analytic implies holomorphic. That is, to have a power series means that you're differentiable. But what about the other direction? What about holomorphic implies analytic? Is that even true? If it's not true, what do we need to add to the mix to get it to be true? Are there more conditions that need to be added? So this is kind of the big questions that we want. So what we're going to lay out today is a reason to believe that there's a way that we can use the Cauchy-Goursat theorem to recover the value of a function, which is kind of strikingly weird to me. So essentially, we're going to be constructing the values of a function by looking at its values on the edge of its domain. And that's not something you can do in real calculus. So this is what we're going to do today. We're going to write down some C. And my claim is that if you give me any W inside that contour, and f is analytic, then I can tell you the value of f at any W inside.
If you know it.
If I know how it acts on the contour, if I can integrate it on the contour, I can also tell you everything there is to know about this function in the interior. Which is, you should think that means that analytic functions are really rigid, because that's an incredible amount of information to get out of what's going on at just the edge of the domain. Okay, so let's begin by supposing that we've got the setup to use the Cauchy-Goursat theorem. So let's say we have a contour C. That's not how you spell contour. So let's start with a contour C, and we'll make it smooth. And for the purposes of our motivation, we can make it simple. And let's suppose it lives inside a domain D, lives inside a simply connected domain. And let's have f be analytic on D. So it's this picture. We have a a set C. We have F analytic on C, like in a domain containing C. So here's our domain D. So the Cauchy-Goursat theorem is going to apply here, right? Cauchy-Goursat immediately implies that the integral around C of f of z dz is equal to 0. Yep.
Does C have to be closed?
Did I say not say closed? I meant to say closed. I drew closed twice, and I did not say it. Yeah, closed. Yep.
What is that first word before inside?
Lives.
Lives. Okay, thank you.
Okay, well that doesn't tell us very much, right? I mean, integrating around the contour C gets us 0 is not a ton of information about what f is doing. So let's suppose that I give you a w. So pick some w inside. Pick w inside of C. And let's suppose that f could be expanded as a power series. There was some way to do that. So this is a big assumption. So we're going to assume f can be expanded as a power series about z is equal to w. So let's assume that that means that we have f of z is equal to a naught plus a1 z minus w plus a2 z minus w squared So one thing that we saw earlier is that if we took the integral of 1 over z minus a around some contour, and a was inside the contour, we saw that this integral was equal to 2 pi I if a is inside C, right? So we did that by direct substitution. The Cauchy theorem tells us that the integral of z minus a to the n dz around that same contour is equal to 0. Right? So if I integrate an analytic function, I get nothing. If I integrate this 1 over z minus a dz by doing the circle contour theorem and integrating around the circle with the parameterization, this turned out to be 2 pi I. So now the question is, could I figure out something to do where I can integrate both sides of this equation and not get 0 out? If I integrate it right now, it's going to be 0, right? Because if you integrate f, well, the integral of a constant is 0, it's analytic, and this is going to be analytic, and it's 0, and this term is going to turn out to be 0, and that term is going to turn out to be 0. Everything's going to turn out to be 0. That's what the Cauchy-Goursat theorem says, right? It's a pile of analytic functions. We integrate them all. They all turn into 0. Is there any modification I can make to this so that something is not 0? Yep.
Divide both sides by z minus.
Oh, there you go. You just discovered it. The most important theorem in complex analysis. Let's divide both sides of this thing by z minus w. We're going to induce a singularity in this function. So we're going to force this thing to be singular at w. So we divide this by z minus w, and we divide this by z minus w, and those cancel. We divide this by z minus w, and this drops to a first power. We divide this by z minus w, and this drops to a second power. And now we have f of z minus w is equal to a naught over z minus w plus a1 plus a2. Good so far? What do I get if I integrate it? Now integrate both sides with respect to z.
Not 2 pi I.
Let's see. So the integral here, integral here. We get the integral around c. It's okay. Now remember, w is inside the contour, right? We've built this contour. We've chosen w inside of it. F of z over z minus w dz is equal to the integral around c of a naught over z minus w dz plus the integral around c of a1 plus the integral around c of a2 z minus w dz and so on. What's that term equal to?
0.
Yeah, it's an analytic function, right? This is analytic in and through C. And this is analytic. There's no singularities here. It's an analytic function. So this term is nothing. This term is nothing. What's that term equal to? A naught's a constant. So I get A naught times 2 pi I. So we have one more big step to take here. What is A naught in a power series? It's f of w, right? If you have a power series for f and you plug w into it, that cancels and that cancels and that cancels and that cancels. Everything in the power series cancels except for the A naught. If you have a power series, f of z is equal to A naught plus A1 z minus w plus A2 z minus w squared and so on. And you actually evaluate that at the center of the series. The only thing that survives is the A naught. But look at what that would mean. That would mean that if you took this, you get 1 over 2 pi I times the integral around c of f of z over z minus w dz is f of w. Which means if you know how this function acts on the contour on the outside, you can construct the value in the middle for any value in the middle. That's weird. So this is called Cauchy integral theorem. Now it's not proved yet, but the thing with complex analysis is a lot of times you can guess what the theorem should be by putting in series and manipulating things, and then you can prove them with different methods. So the Cauchy integral theorem says if f is analytic on C, that you can tell me the value of f anywhere in the interior as a contour integral around the outside. Yep.
Is this just like you define your power series at different points and then you can figure out what your value is?
So what is the issue here? Yeah, so the first thing is, ultimately, we don't know that we can expand power series this way, right? We don't know that yet. That's actually a consequence of the Taylor theorem, which this theorem actually proves. Actually, you guys can tell me the next harder version of this theorem, which is, what if I wanted to know f prime of z? Is there a way I can use this exact same setup to find f prime of z instead? Yeah, if I divide by z minus w squared, then I get a z minus w squared here and a z minus w to the first, and then all the rest of them are analytic. But the other thing we proved when we did those integrals of 1 over z minus a to the n is that if there's a power greater than 1, that also is 0. So it turns out this same exact argument is going to tell us how to calculate the derivatives of f as well. Yep.
So is there a way to prove the Cauchy integral theorem without like using a Taylor series?
Yes, we're going to do that. In fact, this observation here, this is going to be how we get the proof of the Taylor theorem out of the Cauchy integral formula. What I'm trying to show you here is that this does not look like it's obviously connected to the coefficients of a power series, but it absolutely is connected to the coefficients of a power series. Okay? So I'm trying to motivate it, but I'm going to prove it a completely different way. So the idea is we guess what the theorem should be, and then we can't use this argument because it's not a proof, right? We've assumed that the function has a power series at w. We don't know if this exists or what structure it has, but if it did, this would be true. So what I'm going to do is I'm going to save this part, and we're going to prove it. And then after we prove it, we're going to do a bunch of examples about how do we use it. Okay, so are there questions about this motivating thing, right? Again, the idea here is we are trying to tie integration that looks like the Cauchy-Gaursat theorem, this contour integration on loops, together with evaluating f at points and ultimately to the coefficients of power series. Sweet. Let's prove it. I am going to hit you guys for the first time with an epsilon today. But it's actually kind of a cheesy epsilon because it's not that hard to do. Okay. So here's how we start. Proof. Come on, I'm an analyst. I've got to do it at least once. Let epsilon be greater than 0. So, by the circle contour theorem, there exists a circle, say C hat, so that this problem, this integral and this integral are the same. Right, so that's C hat right there. But I'm going to put an extra condition on C hat. So I'm going to reduce this integral to an integral around a little circle around the point W, because I want to use the parameterization. So circle contour theorem lets us go from a general C to a small C hat. And with the one additional condition, there exists a circle C hat close to W, by which I mean, which means in this context that if Z minus W is less than R, we have f of Z minus f of W is less than epsilon. Why on earth am I allowed to say that? I'm saying I can find a little tiny set in the domain that puts tight controls on the behavior of f. It's the definition of continuity. Why is f continuous? An analytic function is automatically differentiable. So the whole chain of stuff here, right? An analytic function must be differentiable. A differentiable function must be continuous. So I can do this because f is analytic, which implies that f is differentiable, which implies that f is continuous. So that little itty-bitty circle that I drew right there, which I'm going to write as z of t is equal to w plus r e to the it, that r is chosen to make that circle so small that f of z and f of w are as close together as you want them to be. Okay. If you haven't seen this sort of approach to continuity before in an analysis class, what you should think is that what characterizes a continuous functions is that small perturbations in input correspond to small perturbations in output. Okay. Well, I would really like to show that these two things are equal to each other. And the way that you do that in analysis is we are going to show that the distance from the integral to the value that we claim that it has, I'm going to show that that's as small as I want it to be. If the distance between these two things is less than epsilon, but epsilon was chosen arbitrarily, that means from an analysis standpoint they are equal quantities, same quantity. This number and this number are arbitrarily close to each other. So this is our goal, is to show that. All right, now some analysis. Okay, so the absolute value of 1 over 2 pi I integral over C of f of z over z minus w dz minus f of w. That's an absolute value out here. First thing is I'm going to reduce this problem to the circle. And then I'm going to do something else. I'm curious if anybody can figure out what I do here. 2 pi I integral c hat f of z over z minus w dz. Okay, now what I want to do is I'm going to write f of w as 2 pi I f of w over 2 pi I. Anybody know why I just uncanceled 1 in that way? I really want to put these together as one integral. But I don't have one. I have an integral and then this f of w floating around out here. If only there was a convenient quantity that was equal to 2 pi I that I could write down. How about 2 pi I is equal to the integral around c hat of 1 over z minus w? That's equal to 2 pi I, right? Just by direct substitution. Oh, okay. So now I get to play this cheese move where I'm going to turn this copy of 2 pi I into the integral of 1 over z minus w. I'm going to leave that one alone. So this is equal to, okay, 1 over 2 pi I integral around c hat of f of z over z minus w dz minus 1 over 2 pi I times the integral of f of w over z minus w dz. After all, f of w is a constant. Maybe it would be more clear if I wrote it like this. Let's leave the f of w out here for a second. 1 over z minus w. That's just 2 pi I, right? So now I've got this f of w floating around as a constant, so I might as well stick it inside the integral. And if I do that, notice I'm integrating around the same contour, and they're multiplied by the same coefficient out front. And they're also dz, and they're over the same denominator, so this is actually equal to the combined integral f of z minus f of w over z minus w dz. It's an algebra trick to kind of mash it all together as one integral. Now I'm going to use the parameterization that z of t is equal to, or z hat of t is equal to w plus r e to the it. I just use this now. So that z dz is, let's just put this, dz is I r e to the it dt. So we're going to use parametric integration. Ow! I'm glad that's recorded for posterity on my my YouTube page. It didn't actually catch me banging myself in there, but it heard the noise. Okay, I'll just delete it out. Okay, so we're using just the regular old parametric integral now, right? We have I'll wait. Okay, so plug in the parametric integral here, and you're going to get the integral of 1 over 2 pi I, integral from 0 to 2 pi, f of z of t minus f of w. Okay, well now z minus w is w plus r e to the it minus w. And dz is I r e to the it dt. Notice everything is still equal. Everything's equal to this point. But now all kinds of nice stuff cancels. There's an I here and an I there. They're in absolute values anyway, but it doesn't matter. They cancel. So the i's are gone. And then there's this r e to the it. That's gone. And we're left with the absolute value of 1 over 2 pi, integral from 0 to 2 pi, of f of z of t minus f of w. So we've reduced the entire problem to the distance between f of z and f of w. But way back at the beginning of the problem, we made this assumption about the distance between f of z and f of w that we were allowed to do because f is continuous, right? So we can crash through with the modulus, or just triangle inequality if you like. So an absolute value of an integral is always less than or equal to the integral of the absolute value. But that quantity right there, we set this problem up so that would be less than epsilon. Z of t is on that circle around the disk. F of w is inside of it. So that distance is definitely less than r. The distance from z of t to w in absolute value is less than r. And so we end up with the integral of epsilon from 0 to 2 pi, 1 over 2 pi. Oh, look, this sounds magical when it turns out to be equal to epsilon. So what have we shown? We showed that if we calculated the distance between that integral and that function value, and we ground through this process, all of which depended on theory that we've built before, that that distance can be made arbitrarily small. And so therefore, these are equal quantities. And that's the proof of the Cauchy integral theorem.
Is that a huge in that last one?
Where?
Oh, it's an epsilon.
This line right here? Oh, that's an epsilon, it's not epsilon. Oh, and then because people insisted last time, I guess I have to put some sort of symbol at the bottom, like a little box with some lines in it or something. Or if you're really If you're really pretentious, you can write quod erat demonstratum. Okay, so that is kind of how these things go. If you've never seen an analysis proof like this before, this is typical of the form, right? Where you assume that two things are close together and you show two other things are close together. But notice, we basically use everything we've done so far to do this. And we never referenced a power series in the course of doing so. And this is going to be what we use to build power series coefficients when we get to Taylor series. Okay. So now what do we do with it? Great, I just called it the most important theorem in complex analysis. Are there questions about the proof before we go on? Other than are you responsible for it? Of course the answer is no, you don't have to be able to prove this, but it sure would be nice if you could. It's a nice proof. All right, so let's use it to integrate some stuff. So we'll write down permanently now that we know that with the correct hypotheses, that the integral around c of f of z over z minus w dz is equal to 2 pi I f of w, or you could have the 1 over 2 pi I version of it if you want. Or 1 over 2 pi I integral around z of f of z over z minus w dz is equal to f of w. So I'll tell you that the reason that I went through the motivation at the beginning is because I think if you don't see that, this just looks absolutely mysterious. Like what is this and why? Like where does it even come from? So keep in mind, it's not magic. This is just trying to pick out a power series coefficient. All right, here's example 1. Oh man, I'm going to do a sweet contour integral here. Not yet. Okay, example 1. Integrate cosine of z over z dz, where I go around the circle of modulus 1. Well, you should already have your antenna up, because you can probably tell that math books and math professors hide very easy problems by requiring you to notice things like z is equal to z minus 0. The integral around the circle, z is equal to 1 of the cosine of z over z minus 0 dz. If only there was a theorem that we could use to evaluate something like this when this point is inside this contour and that's an analytic function. So you check your conditions. Cosine of z is analytic inside and across the modulus of z is equal to 1 because it's an entire function. It's analytic everywhere. 0 is inside the circle of radius 1. And so the Cauchy integral theorem applies. So CIT applies, which means that the integral around that circle of the cosine of z over z minus 0 dz is 2 pi I times the cosine of 0, which is 2 pi I. So what you're looking for with a question like this, your suspicion when you start seeing denominators that look like they induce these sort of singularities is that this kind of thing is happening. What? What? Does it seem lame? It is silly. Of course it's silly. I have to show the silly ones before I do the hard ones. Here's another easy one. The integral around c of z squared over z minus I dz, where c encloses I, is what? Well, z squared is an entire function and thus analytic on the circle. So this must be equal to 2 pi I times z squared evaluated at I. Let's be more I'll be slightly more formal about this. F of z is equal to z squared, which is entire. I is inside C. So the integral around C of z squared over z minus I dz is equal to 2 pi I f fi, which is 2 pi I times I squared, which is minus 2 pi I. Yep.
Is this like more useful for calculating integrals or for like figuring out the values of functions?
It's both actually. It turns out to be both,
Okay.
right? So it turns out to be the case, the fact that this evaluates functions, normally what happens is we use this in the backwards way, where we use the fact that we can evaluate the functions to solve for integrals that are structured in a certain way. That's really the direction this usually goes. So like what we're doing here, we're evaluating integrals by plugging numbers into functions. That's typical of this sort of applications. What if I was outside of C? What if I do exactly the same problem? After all, your math teacher might try to trip you up and say, the same exact problem, and now I is outside of C. The integral around C of z squared over z minus I dz, but I is outside of C.
0.
Why? It's a simple closed curve. It's analytic on the inside. Cauchy-Goursat theorem says it's equal to 0. I mean, no math professor would ever try to trip you up by putting minor changes in the hypotheses of a problem. That would be mean. I mean, I don't know if I would actually do that, but I'm not trying to imply anything by saying that. About myself. I might be trying to imply things about other people. Okay, so let's do something with a little more heft. Let's look at this function. Um, 2z plus 1 over z squared plus z dz, where we have a contour of radius 1/2. Now you might ask, why are we doing all these computations of rational functions and integrals that look like this? These aren't just cherry-picked examples. The theory of evaluating and working with, there's two reasons. The first is, the theory of evaluating and working with rational functions is basically what all of like huge pieces of engineering are built out of. That's the first thing. And the second thing is, it turns out that you can approximate entirely in the land of complex analysis with rational functions. So rational functions are the most natural sort of approximating functions. And so understanding rational functions is the key to understanding all the rest of them. Well, let's see what's going on here. Where does this function have asymptotes? Z is equal to 0, and z is equal to -1, but the circle is only radius 1/2, so the picture we're looking at here is there's an singular point at 0 and another one out here at -1. And the contour looks like this. So the game then becomes, I would love to evaluate this using the Cauchy integral theorem, but I need an analytic function to do it, and that function's not analytic. So what we can do is we can rearrange this function into a piece that is analytic on the interior of this, and a piece that represents evaluation of 0. So the move is that we rewrite the integral like this. The integral over C of 2z plus 1 over z squared plus z dz. Now I could use partial fractions if I wanted to, but this is going to let me do this. The integral of 2z plus 1 over z plus 1, all divided by z minus 0 dz. This function, notice all I've done here is I've peeled off like a bunch of this stuff and stuck it in the numerator. And the reason I did that is because that function is analytic on that set that we're working with, right? This function only has a problem at z equals -1, which is not in this inside the contour. This is analytic inside and across C. And so this is equal to 2 pi I times that function evaluated at 0. 2 times 0 plus 1 over 0. which is 2 pi I. So clever rearrangement of functions turns out to be a thing that is useful to be able to do. And now we're going to draw a clever contour that we can use. Yep.
Is it just a coincidence then that if you didn't rearrange the functions that you would actually get?
It is absolutely not a coincidence. It's not. If you took this thing and you partial fractioned it, you're going to end up with a term that has something over z and a term that looks like something over z plus 1, right? And each one of these either will evaluate to 0 or 2 pi I, depending on how the contour falls. So one way of thinking about what these contour integrals are doing, they're counting the number of times that an order 1 singularity is inside the contour, right? If there were 2 inside, you expect the answer to be 4 pi I. If there's a single 1 inside, you expect the answer to be 2 pi I. So this has to do with counting the number of poles. In fact, this is one of the places where this links up with abstract algebra and group theory. Okay, what if I ask the same question, but I ask it now for the contour where the modulus of z is equal to 2? And now we get to draw, this is our first venture into the world of drawing awesome contours to solve a problem. Okay, so same exact question, but now the contour 2z plus 1 over z squared plus z dz. But now we have this situation. So I've got a singularity at 0 and a singularity at minus 1. But then the set that I'm integrating over is this one. Here's c. So last time what we did is we broke that function up into 2 pieces. We sorted the 2 pieces of the integral out, and one of them had an asymptote here, and the other one had an asymptote there. I'm going to show you how to do it using this idea instead. So we're going to build a new contour. This is my favorite part of this, like this first part of complex analysis. That contour is terrible because I can't use the Cauchy integral theorem, so I'm just going to make my own. I'm going to write down a simple, closed, piecewise smooth curve in here that takes the interior and makes it simply connected. And I'm going to do it like this. Okay, so first we're going to build a contour called S. And what S is going to do is it's going to do C first, so it does C. So you go around and you do C. And then you go inside towards 0 on something that we'll call, I don't know, L in, I think is what Johnston calls it. So we're going to head towards 0 on the way in. So first we do C, and then we do L in. Then we're going to do a half circle around 0. So we're headed this way, and then we come in like this, and we go around. And then I'm going to head from 0 to 1 with another section, which I'll call M in. So first, so it's L in, then the top half of a contour that I'll call C0 because I'm wrapping around 0. And then I'll union that with something called M in. Then I'll do a little circle around minus 1. Call that C1. So I had it this way. Then I'll go back out with M out. Then I'll do the bottom half of the circle around 0. And then I'll get back out to the curve C again with L out. Why on earth did I do that? Yep.
I was just wondering, the arrow by C, is it going counterclockwise?
So we go here, we go up to this point, we go in, we go this way, we go this way, we go around, then we go out, then we go this way, then we go out, and we come back to here. L in should be like, you can think of it as being below. It's the same line. Those are supposed to be the same line. Right? It's deceiving because the way I drew it, it looks like that there's a gap in between and the arrow goes the wrong way here, but these are the same line segment and those are the same line segment. Okay, well that's a closed loop. And the interior of it is simply connected. So what's this equal to? Oh yeah, it's 0 by the Cauchy-Goursat theorem, right? It's a simply connected curve with a, yep.
Are you double counting space? with the way that you drew the arrows.
What do you mean?
Well, we traverse,
So what you should think here is that this is, if I had drawn this with these flipped and these flipped, this is oriented, oh, I've got my orientation backwards here, don't I? Okay, I'll fix it. Man, why wave my hands a little slightly less. Okay, let's actually make this oriented correctly. Okay, it's always to the left, right? So we should go in here and then around this way so that we're to the left, and then around this way so that we're oriented to the left, and around this way so we're oriented to the left, and around this way and this way. And now my orientation is consistent with always being on the left-hand side where I'm not twisting around. Thanks for pointing that out. It's important detail. Okay, the answer is still no, I'm not double counting anything.
so then,
I went around it.
okay.
So, this integral is nothing because this region that I've put inside here is simply connected, and the function is analytic inside and across that simply connected region, right? The only bad places are here and here. So the Cauchy-Gaussat theorem says it's equal to 0. What can you tell me about the relationship of this integral and that one? They're opposite because it's the same integral but on oppositely oriented paths, right? And what can you tell me about the integral on this path and that one? Oh, so look at that. So that means that the integral around this big contour S, which is equal to 0, 2z plus 1 over z squared plus z dz, is equal to the integral around c0 of f plus the integral around c1 of f plus the integral around L in of f plus the integral around f on L out plus the integral on m in of f plus the integral on m out of f. But those cancel because they're opposite, and these cancel because they're opposite. And I actually know the integral of f around c naught and c1 because I can just apply the Cauchy integral theorem, right? The Cauchy integral theorem applies on c1. On c1, I can do that denominator sorting trick. The integral on c1 of 2z plus 1 over z squared plus z dz, well, around c minus 1, I could write this as the integral of 2z plus 1 over z plus 1, which is 2 pi I times 2 times minus 1 plus 1 over minus 1, which is 2 pi I. By the Cauchy integral theorem. Yep.
The way that we've drawn C1, though, doesn't it not point to the inside of...
I mean, it's the negative. The thing is that what we're going to calculate is going to be the negative, but we're flipping the orientation. Like,
Right.
It's actually the integral of minus the C1 that we're computing.
And that affects our answer, though, right?
But it'll put a negative in it because we're orienting backwards, but that would put a negative here, and then when we flipped it, it would turn out positive.
Got it.
This integral, around that circle, you can do the integral around C0 of 2z plus 1 over z plus 1 over z dz. That function is analytic. So this is also, it's 2 pi I times 2 times 0 plus 1 over 0 plus 1, which is also 2 pi I. And perhaps unsurprisingly, that means that the whole integral is 4 pi I. This is characteristic of what complex analysis is going to look like now. A lot of it is careful construction of these things in order to compute the integrals. Yep.
Is that first integral on the top x is p over c1? Or
This one,
yeah, where,
it's supposed to be. This one is supposed to be around this point because the rest of the function is supposed to be analytic there. Right. This function is analytic around C1. Did I not put that there?
oh, okay.
Yeah, it's C1.
Okay.
Yeah, so this function is analytic around that thing, and so we can just use the Cauchy integral formula because we have one place to evaluate. This example is done in detail in the book if you didn't follow what I did in here, okay? But the idea of cleverly constructing a contour and decomposing an integral into pieces like this is going to be a skill that we're going to be using throughout the rest of the course. So when I give you homework on this, the thing to do is to try to practice thinking this way about decomposing things, pulling functions apart and moving. It's core to like working with complex integrals. and essentially leveraging analyticity. All right, I'll deal with the quizzes if you guys have them. I can take those now.